Hello and welcome. Today I'm gonna explain the algorithm behind the smooth terrain, and this is version 2.0 as you can see up here. The previous videos has been using version 1.0. I'm currently developing version 2.0 since I've found a lot of improvements in the version 1. So let's begin. Why? You might ask yourself, why would I do this? There are a lot of voxel terrains out there. One reason is that the Minecraft terrain, the block voxel terrain, is not that easy to drive on. This terrain is easy to drive on since it's smooth. It's smooth looking, it's more natural bended terrain, which is nice. But I don't want to go all the way to marching cube or some algorithm like that, because then you lose a sense of removing, because a lot of those algorithms feels like you're smoothing or absorbing terrain in a kind of non-natural way. So I don't really like marching cube based voxel terrains. So that's the reason why I did it, and also it's a lot more efficient when it comes to data, since it's just using big chunks but it's still smooth. So originally I called this flow out terrain, but then eventually it became flow up terrain. My original idea was that I wanted a cube on top of other cubes to flow out, to make it look like a pile of dirt. It's not just a cylinder, it will flow out in a pile. But eventually I realized that the optimal way was using flow up terrain instead of flow out. And if you look here, the standard example of a flow up terrain, you see no flowing up, but if you have a cube next to the cube, you see the top, this is the top, flows up to smooth out the surface. And you see this is the side view. And if you have 3 blocks in top next to the one we are evaluating, we flow up 2 blocks, and this is also the maximum for this algorithm. So it's a 2 steps flow up terrain. But if you look at this scenario, if I would have used flow out terrains, this cube and this cube must communicate how to flow this out to bring this side into existence. That's much more complicated than just flow this up and make it smooth. And here you also see another example. Here we missed the cube here, but we still use the flow up, and this is to smooth out and connect the terrain that will reduce the amount of blocks floating in the air. And here you can see the 4 height, and you can see there's no smoothing here. And I didn't really thought this was good enough, so I also added 4 heights on the cube, so it's 1, 2, 3 and 4, so it's 4 different standard heights. The data that the blocks are stored in, normally they have an ID, but I've also stored a lot of data about the block in the ID for really fast fetching. And then I have stored data in a dictionary for slow fetching. I will go over this now. First, the ID. As you can see, the ID is a byte, a struct, which contains 1 byte. So each block is 1 byte big, and it's a struct. That struct has functions. It has is_transparent, then it checks if the first bit is set to 0 or 1. And just as a reminder, the standard block is the 0 block, the 0, 0, 0, 0, 0, 0, 0, 0. That means that this is air. So in is_transparent, bit 0 will be 1 for non-transparent and 0 for transparent. Flow up I will explain in a little bit, and flow down you have already heard about. And then the heights, which is 2 bits, 3 and 4, and then we have the block number 5 to 7, and this means that we can have 8 different blocks of exactly the same configuration of height, flow, up, flow down, and transparency. So, flow down. I've talked about flow up before, but flow down is everything that is on top of a flow up surface or a normal surface. So if you look at this example here, you have a flow down on the top of a flow up. You see the grass position it smooth on the top. So the algorithm works like this. It looks in the flow up block and then it builds the flow down block above the flow up block. You can look in here also. You see 2 flow down blocks and then 1 flow up block. This is this flow down block that's positioned this grass on top of this cube, which has moved its surface up all this way. And to make it also possible to adjust the terrain, you can add an air block which is not flow down. Then it will move this slope a little bit lower down, so you'll degrade it 1 step. So you can remove even if there isn't any real block there, as you can see on this last part. And this is side view still, so no confusion. I will also write top view on those slides where it's applicable. Transparent. I will only skin the visible faces. So if a face is covered by another face which is not transparent, that face will not be drawn. So, data stored in dictionary. This is slow. So it's anything that is 1 time per block fetch, like texture data, chunk texture, have top blocks. Have top blocks is that if we have, or we can start with chunk texture. Chunk texture is that we have a big texture instead of 1 for each block. So if you look at the train before, you can see that it repeats every 16 block, but it's really hard to see since it's 16 blocks wide and it's really detailed texture, so it's not like big rocks or so on. So it's a smooth way of making it look like it's an infinite big texture. And it also reduces the draw calls and the amount of not draw calls, the polygon count, since we can do merge polygons. I'll go over that in the future. And have top blocks. You know the standard dirt grass blocks in Minecraft? That's exactly a top block. So if you have a big chunk block, you have a top block on top of every empty transparent block. So if you have a chunk and then you have a transparent above it or some other data, then it will have a grass side, for example. So this is the way to signal that to the algorithm. So I will go over the generation and skinning and shadowing now. Generation of the terrain will not be explained in this video, only the skinning of the placed blocks. So we will dig into skinning. This is the focus of this video. I will also mention something about shadows and biomes and so on. Skinning. Skinning is divided into 4 parts. First you generate the data, not the blocks, it's the data for the skinning. Then we calculate corners, test visibility of the faces, and finally we add the polygon and the textures. So, generating data. Flow up height, FUH, X. X is how up the flow up should look, and S is if it's solids only, if it's opaque, so to say. Max flow up height, it's the flow up height at the current block. So if you have, for example, one block to the immediate left, then the flow up height will be 3 at that block. We can go to the first slide. Here, see, this block will have maximum flow up height for this block of 3, because this block can flow up 1, 2, 3. But if you look at this block, it has a maximum flow up height of 3 also. So we will continue. The maximum a column could flow up. Yeah. So we cache the data. We cache it in a big 18 by 18 by 22 matrix, and this is since the cube is 16 by 16 by 16. We must look 3 blocks up and 3 blocks down from the current cube to get all the data about the flow up and flow down data. And in each position in this, you have a long int which contains all this data, and it's a struct, and it contains different connections, and this is properties if you're not familiar with C#. So the FUH3 float is really just stored as a 4-bit value, because the blocks, as you remember, can only have 1, 2, 3, and 4 in height. So flow up height can at total have value from 0 to 4 times 3 equals 12. So with 4 bits you will have a value of 0 to 15 to play with, so it's enough to store it in that. And the same goes for the rest of it. You can just figure it out. The top corner is also the same. It's the position of the corner. So if you have a block which is 1 height, then all the top corners will have value 1 in the float. But it's still stored as a 0 to 15 bit value. And all these structs also have byte access to them. So you can do all the math in byte world instead of float world, which is a little bit faster, and you don't need the conversion from float world to byte world, because that takes time of the processor. Optimization is everything in this part, because this is the part that will run many thousand times per frame. In worst case, no, hundreds of times. Yeah. Well, it's a lot of time still. So, calculating the corners. This is top view, so you don't get confused. And the C is the current cube we are evaluating. A and B are the neighbors. They are directly adjacent to C. Then we have AB, a diagonal cube. And we'll briefly explain this. But first, if you look at this, you can see that A and B is positioned around the normal cube. You see the cube in the middle. So we just turn the algorithm around 4 times. So it's the same algorithm for each corner, but just turning it 90 degrees per corner. So it's performed 4 times, 1 for each corner, or corner column, I would say. And this is calculating the top value. The bottom value comes from either if it's a flow down value from the previous flow up, which called the flow down to be built, or it's set to 0 if it's not a flow down value. So, calculating the corner. This is the heavy part. Bear with me. We have a value, height x, which is calculated as the maximum of A, flow up height x, B, flow up height x, AB, yx, where yx is calculated as AB flow up, it should be U there, flow up height x, which should be less than maximum of A, maximum flow up height, B, maximum flow up height. And this means if, we could say, this will compile in a standard C#. I don't remember the name for this kind of writing, but please post it in the section below if you remember. But yeah, if this is true, then we add ab dot flow up height x u here also. Otherwise we just add x minus 3. And then we have corner height, which is the actual value. Here we take the height 3, which is greater than 1. So if the corner is higher up in the air than 1, which is the standard block height, then we use the height 3 value. But if it's not, we use the height 2 plus 2 value. The reason for this is that if the block has only flown up to the standard height, then it might be that the block next to this block was empty, and then you must look one step up. You remember to connect the grid, connect the blocks which are floating sometimes. I'll go and show you up here. This case, because then this block will find nothing here, and then we have to go and check it up here. That's where we look one step higher up. So this is kind of hard to get, I guess, and this is an algorithm that I've been thinking about very much. Many hours have gone down into these 3 lines. But what it's really about is that you take the corner value and then you check if, I will explain this line right now, you will test the maximum flow up height that you can find. So in this case, if A is 2 and B is 3, 4 is not a valid value, because if it's bigger than 3, it's automatically returned as 0 value, or minus 1 if it's height 2. And also the AB value is included. But the AB value is kind of complex, because if A and B is flowing up to AB, then C should flow up to A, because otherwise it will be strange in the train. So it's really about, if AB is very high up and then A flow up to AB, then C should have the possibility to tag along and also flow up, even though A isn't by default flowing up as high as AB. I hope that makes sense. That's the ABYX part. And the X here is because if you look one step above this level, you cannot have a corner height of 3 plus 1, because you see this plus 1 value here. You want to have a height value of at maximum 3. So therefore we look at the block above, if that has the surrounding A, B and AB of these values. As you can see, we don't do any calculation on the C value on the block above, only A, B and AB in relation to the C block here. You see here, for the block above. So in the case that you have in the first slide, we'll go back to that one. this will first in turn return the A. We can call this the C block and this the A block. Side view, the other was top view, so you don't get confused. Then you see that this value, this has no flow up height because it's an empty block, and this block has flow up height. So this should really be connected like this. But in this case, this block will just flow up to 1, and then when you compare it to see if 1 is greater than 2, if this height is greater than 1, but it's not. So then we also check in for this block, this cube, the values of A and the B and C, A, B, which are not visible here. So in this case, this would be A one block up. I hope this makes sense. If it doesn't make sense, just tell me and I'll dive in and try to explain it one more time, because this is really tricky, I get it. But I don't really know how to explain it, because this is how I think about it. So, let's continue. When we have evaluated the corner height of all 4 corners, we have a cube with bottom corners and top corners, and then we should test the visibility of the faces. So, the visible faces are only the faces that the player can see. You see this black line. Inside here, it's not visible. You don't have to show it. You don't have to make it. How do we test the visibility? It's quite easy. You remember that we cached all the data. So for the case of the C, we just calculate the corner values of first block 1 here, which is 0 in solid height, and then we calculate, so this is a solid flow up height block by definition, and this is air block, which is not flow up height, have no flow up functionality. So this means that the block here is empty and will return 0 in flow up height in the corner values, and then the block 2 also has 0 in the corner values, but block 3, it has a top corner value that is exactly in level with the corner value of C in this side. Therefore you don't have to generate the C faces. And in the case that the C would be generated before 1, 2 and 3, 1, 2 and 3 corner values are first generated and stored, and then the C goes back and look at the 1, 2 and 3 values. I hope that makes sense. Let's continue. Add quads and textures, block type side configuration. The block type, which is data stored from the dictionary for each ID, is a configuration of the sides. So, for example, if you have seen the bushes, that's one configuration, and then the standard solid block, the stone and the grass, the ground and so on, that's one block. And you see the grass on the ground, that's also one type. So there are many different types. The quads are cached in a 18 by 18 by 22 matrix. They could really be stashed in an 18 by 18, 16 by 16 by 16 matrix, but it's kind of more convenient working with the same numbers, and you don't have to convert it, or I'll optimize that in the future if it's any beneficial, but mostly it will just give small errors where I've missed the 17 value is that the 16 value of the other matrix, and keep the matrix the same size, makes it a lot easier. And also store the connection to neighboring blocks quads of the same type. This is so I can merge textures. So if I have two textures and I want to merge them, I can easily do this by just looking at the connections. And this is what will be done in the next step. I'll store both aligned. A line texture is that if you look at the type, if you have a block, look at the cursor. If you have a block like this, and then you have a slope like this, and then a block like this, then this is not connected. These are connected but not aligned. But if you have a block like this, and then this and this, then you have three blocks which have a top side which is aligned. It means that this three blocks top side can be merged into one big polygon. Quads to polygons. Connect aligned quads to polygons, then not connected will not be merged to polygons. They will only be used for removing vertices. The vertices and the UVs are stored in an array. Wait a second. Yeah, now I remember. The int here is because we need to keep track of the vertices, I believe. This is kind of complicated. I'm still working this out at the moment. Since this is version 2, I didn't do this in version 1. I only used one per block polygon. This will be a lot more restrictive on the use of polygons. Remove duplicates of not aligned vertices from the same textures. And we use ints, so if we have a vertices and we're removing it, we are storing an int by that vertices in the cached data. And the next time we want to compare and see if any of the other vertices are already stored, we can just check up that int value, which will be used by the indices, the polygons, the triangles. And well, when we have this arbitrary big polygon, we use triangulation of that arbitrary polygon, and we use most likely some monotone algorithm, which uses some lines and divide the polygon along those lines, and then use those monotone polygons. Well, look up it on YouTube. Triangulation is pretty straightforward at this point when we have the polygon connected. So, shadows. Shadows gives depth. I have some pictures of my terrain in the early stages where I didn't have these shadows, and it was a lot of problems with depth because you couldn't really tell if that belongs to that or that belongs to that, or because the shadows just weren't there, so everything was just a green blur. So even if you don't use real shadows, which I will not use in the version 2 because I will use Unity's built-in shadows, which I think will make it faster and look better, because I move a lot of the shadow calculations from the CPU to the GPU, and normally the GPU is not that heavily loaded, especially if I do the polygon merging, and I think it's a great benefit for using real shadows instead. But I still will use some kind of shadow for the corners of everything. So if you have a deep corner, it will be a shadow in that deep corner. And all this is stored in color data array. So all this has so far been done in the thread, in a separate thread. This is important because your normal CPU has 4 cores, or well, new computer has 4 cores, and there will be a lot of cores more in the future. And this can only be used if you thread your work. So the last step of this algorithm is to unload all the graphical data. Vertices, UVs and colors are already stored in arrays, so it's just transferring those arrays to the mesh filter, the mesh collider. And it's not the same arrays, only part of the mesh filter will be stored in the mesh collider. So you can have bushes you can run through and so on. Make the chunk object unload the graphic data. Yeah, that's pretty much it. So we're done. We're not using AABB, or we're not using our own AABB, axis aligned bounding boxes, which is used for normal collision. We are using Unity's default. This makes it possible to use Unity's default collision system, and you can just drop anything from Unity straight into this terrain. It will work right out of the box. Low polygon count, which increase the speed over a long time, but it's one-time cost in the beginning, the first frame when you build it, because you have to merge the polygons. This could be a tweak to turn on and off, so if you really need to make the terrain really fast, then you can turn this off, and then as the terrain has built up into decent level, you can go over it again and rebuild it with low polygon count. Some optimization maybe in the future. So biomes, you say. Right now I only have 8 different blocks for each block type, and that's not much, but since I will be using a matrix of probably byte from top view, and then I will have a 1x16 byte height array to store the biomes. So I will store the biomes in a virtual matrix space, I could say, and then depending on what byte values I will get, those will correspond to different biomes. Pretty much it. So if you have a frozen landscape, you can make this biome by defining the top view, and then the height, make it possible to make high up on the mountains where the snow normally, where it's colder. You can use this height column to define the biome. So both the value from the top matrix and the height, corresponding height column, define the biome. This is the way I think I will implement it. It's not fixed yet, so any comments on this would be most appreciated if you are into the subject. Thank you for watching, and I gladly answer any questions. Just post below. I guess you have understood about most of it, but maybe some of the algorithms part in the middle with the math was kind of complicated. I don't know how to explain it better, but I will really try if you didn't get it. And any questions, ideas and so on, really appreciate it. This is the version 2 that I will make. I haven't made it, so your suggestions will maybe be implemented. Thank you.